So you're a physicist and you want to understand, say, an atom. Now, in a perfect, tidy universe, you could just solve the equations perfectly. But here's the thing, reality is messy. It's complicated. So what do you do when the math gets way too hard? Well, you pull out a seriously powerful tool called perturbation theory. And believe me, it's one of the absolute cornerstones of modern physics. And to really get our heads around this, we're going straight to the source. We're diving into chapter 17 of R. Shankar's classic textbook, Principles of Quantum Mechanics. I mean, this is the book where so many physicists first wrestle with this essential technique. So let's break it down together, step by step. And this really gets to a central question that's honestly bigger than just quantum mechanics. It's about how science, all of science, deals with the beautiful messiness of the real world. You see, when a perfect exact answer is literally impossible to find, you've got to have a clever strategy, a way to get an answer that is incredibly, incredibly close. Okay, so in the quantum world, the list of problems we can solve perfectly, it's shockingly short. I'm talking you've got the free particle, the harmonic oscillator, the hydrogen atom, and, well, that's pretty much it. Almost everything else you can think of, from more complex atoms to particles sitting in magnetic fields, is, from a purely mathematical standpoint, unsolvable from the ground up. So here's the core strategy, the game plan. We take the big equation for the system's total energy, physicists call this the Hamiltonian, and we split it into two parts. First, you've got the part we can solve perfectly. We call this the unperturbed system, or H0. Think of it as our perfect hydrogen atom floating all alone in a vacuum. Then, we add in the messy real-world complication, like an electric field. And that small, annoying addition, that's what we call the perturbation. All right, so how in the world do we handle this messy complication? This is where the magic happens. This is where the perturbation cheat code comes into play. It's this brilliant, systematic method that lets us start with a simple answer we already know, and then, piece by piece, calculate how that answer gets tweaked and changed when we add the messy part back in. Okay, so here's the more formal idea. We're not even going to try to solve the hard problem from scratch. No way. Instead, we take the nice, clean answer we already have for our simple system, H0, and then we calculate a whole series of tiny corrections that tell us the effect of that little nudge from the perturbation H'. Now, the math strategy here is just so clever. We basically assume that the true, complicated answer is just our simple answer, plus a bunch of corrections added on top. The first term in the series is our starting point. The next term, that's the biggest correction, the first-order one. Then comes a smaller second-order correction, and on and on. It's like each piece we add gets us closer and closer and closer to the actual real answer. Now, for most real-world problems, the biggest, most important chunk of the change comes from that very first correction. It gets you most of the way there. So the big question is, how do physicists actually calculate it? And the answer is this beautifully elegant little equation. Seriously, this is one of the neatest results in all of quantum mechanics. The first correction to the energy is just the expectation value of the perturbation. You can think of it like this. It's the average energy shift that the simple original system expects to feel from this new complication we've added. As Shankar himself puts it so perfectly, we're basically just asking a simple question. From the point of view of our original, unmessed with state, what's the average effect of this new thing? That average value gives us our first, and often our very best, estimate for how the energy is going to change. But it's not always so simple. Of course not, right? Take a harmonic oscillator. You can picture it as a tiny quantum spring, and stick it in an electric field. Well, because of the system's beautiful symmetry, that first-order correction, the average energy shift, turns out to be exactly 0. Now, that's not a dead end. It's a clue. It's the universe telling us that the real change is more subtle, forcing us to dig a little deeper and calculate the second-order correction to actually see what's going on. So far, this all seems like a pretty straightforward recipe, right? But there is a critical situation, a trap, where this entire approach just completely falls apart. I mean, it spectacularly breaks down and leads to total mathematical nonsense. The whole problem comes from something called degeneracy. This is what happens when two totally different quantum states just happen to have the exact same energy level. You can think of it like having two completely different keys that can somehow unlock the exact same door. This is actually pretty common in quantum systems, and when it happens, it totally breaks our simple formula. And here's why it all goes wrong. The formula we use to find the correction to the quantum state involves dividing by the difference between energy levels. Well, if two states have the same energy, that difference is zero. You end up trying to divide by zero, the cardinal sin of mathematics, and the whole thing just explodes. You get a nonsensical, infinite answer. It's a massive red flag, basically a mathematical scream for help, telling us we've missed something really, really important. But don't worry, physicists are a clever bunch, and they figured out a fix for this. It's a more sophisticated, more powerful version of the theory that's designed specifically to handle this thorny challenge of degeneracy. This solution is called, fittingly, degenerate perturbation theory. And the core idea is actually pretty simple. It says that when you have a whole group of states that share the same energy, you can't just pick one at random and start. The perturbation itself is picky. It will choose a very specific combination of those states to work with. Our job is to figure out what those correct combinations are, the ones that are stable when the perturbation hits. So here's how it works conceptually. First, you round up all the troublemakers, all the states that share the same energy. You treat this little group as its own mini problem. Then, your goal is to find the special mixtures of these states that play nicely with the perturbation. Once you find these stable states, they become your new correct starting point. And when you use them, the old formulas start working again and the math just stops exploding. Now, I know this might all feel like some really abstract mathematical gymnastics, but you have to understand, this tool is what turns quantum mechanics from a cool theory into a predictive science. It's the bridge that connects the blackboard to the laboratory. It lets us go from pure theory to the real, measurable effects we can actually see. I mean, why should you care? Because this isn't just theory. You've heard of the Stark effect, right? That's when an atom's energy levels literally split apart in an electric field. We can calculate that split perfectly using perturbation theory. It's also how we explain the fine structure of light coming from distant stars. These tiny, tiny shifts in energy are like fingerprints of deeper physics, like relativity and spin. At the end of the day, this theory is how we know that quantum mechanics actually works. And this leaves us with a really fascinating, kind of mind-bending final thought. Perturbation theory, it's not an exact solution. It's just a ridiculously good approximation. So if our absolute best, most precise predictions about the very nature of reality are all built on an infinite series of corrections, what does that say about the universe itself? Is reality something we can ever solve perfectly? Or is the complete answer always just a tiny bit out of our reach?